By the way, in nearest neighbor search, we look for the objects in the dataset whose distance to the query point is the smallest. In many modern applications, the dimensionality and the sample size of the data are so high that the running time of the exact nearest neighbor queries becomes non-trivial.
For example, we might want to use nearest neighbor search to find similar content on the internet. In these cases, we may have millions of data points and a dimensionality in the hundreds of thousands.
However, in the application areas such as robotics and internet or mobile applications, where fast response times are critical, a query time of even few seconds is often too long. This is why approximate nearest neighbor search is often used in these applications. Here we represent the multiple random projection trees algorithm, which gives very accurate results significantly faster than linear search and is tailored especially for the high dimension, high sample size case. The algorithm can also be easily and efficiently parallelized, yielding even more significant performance gains.
When building a random projection tree, we first take a random vector and next project the data points into this vector. Then we choose a split point. Here we use the median of the projected data. This creates a division of the original data into two subsets. This process is then performed recursively for each subset until a predefined maximum number of points per subset is met. Here we set this limit to 3, so subsets CEG and ADH are not split any further. Finally, we split the other subset into smaller subsets Fij and BKL. The splits form a tree structure where each split divides a node into two child nodes. At each node, information on the random vector and split point need to be stored so that query points can later be routed to correct leaves. When answering a nearest neighbor query, we only consider the data points in the same leaf with the query point. Here the query point falls into the same leaf with data points A, D and H, and the algorithm returns D, which is the closest of them. The true nearest neighbor I resides in another leaf, so the algorithm fails to find it. However, if we build another random projection tree, the different random vectors lead to a different division of the space. Using this tree, the query point falls into the same leaf with the true nearest neighbor I.
So, we conclude that by building multiple trees with the same leaf size, we can improve the accuracy of the results significantly. The downside is that the running time of this approach has linear dependency on the number of trees being used. The query time consists of two parts: the time it takes to route the query point to a leaf in each of the trees, and the time it takes to perform a linear time search in these leaves. When a moderate number of trees is being used, the query time is dominated by this linear search in the leaves. In our research, we decreased the leaf size proportionally to the number of trees, so that the total number of data points in the leaves where the linear time search is performed is approximately the same as in the one-tree approach. This way, the query time remains approximately the same, but our results show a significant improvement in accuracy